Okay, guys, so today we're gonna talk about well control course, IWCF course, level 4. So let's start. It's your turn to have a communication with you to introduce yourselves, name, job, and experience in oil field. So let's start by Anil. Could you tell me more about yourself, Anil? Name, job, and experience, and if you have this course before or not. Anil?
I think he is busy right now.
Okay, so could you start per K?
Sorry, I am back.
Okay, we need a quick brief about you.
Okay, sure. My name is Anıl Akıncı. I was born in Istanbul, Turkey, and right now I am working as rig manager in United Petroleum Company. I have like 2 months of experience right now. I am a new graduate. I graduated in October 2020.
Okay. Have you passed this course before?
Yes, actually, not exactly this course, but in last semester of my academic career, I get a course named Pressure Control, and it was focused on exactly same topics as this course, IWCF course.
Okay, but this is your first time to have IWCF level 4,
Yes.
right? Yes. Okay.
Yes.
Okay, good. And per K?
My name is Berkay, and I'm also rig manager at Güney Yıldız Petroleum. And it's my first month in the job.
Okay.
And I'm also graduated from Middle West Technical University from petroleum engineering. And that's all.
Okay.
I
So
also took the same course named Pressure Control with tunnel.
okay.
And I haven't took IWCF yet.
Okay, good. So let's start. First thing, we need to talk about startup and the end times. And I will mention, we will handle it with you today and tomorrow and all course days. We have course material, number 4, this one. Course material, I think you have exercise book, IWCF exercise book. Also, you have quiz book and formula sheet. Also, you have Excel sheet, right? You have all of these material.
Yes, we have.
Yes.
Okay. Then about lunch and breaks, as I mentioned, we're gonna handle it with you during conducting the session. After that, we're gonna talk about course objectives. So course objective, we have 2 things. First thing is to increase candidate operational knowledge of well-controlled procedures and killing operation. During this course, we gonna face a key topics and key definitions. So we're gonna talk about the cake type, blowout, if we didn't control and manage the situation. So we're gonna face something called the blowout. Then the type of the barrier, something to prevent the cake and the influx to reach the surface and to enter the well. So we're gonna talk about barrier and barrier classification, how to pressure test this barrier, how to check this barrier is able to prevent formation fluid to enter the well and prevent formation fluid to reach the surface. Then we're gonna talk about key pressure definition, like hydrostatic pressure, formation pressure. What is the causes that cause formation pressure to be abnormally pressure? Okay, we have many causes. Then gonna talk about the cake warning signs. How can you detect the cake? We have some signs. If you found any of them, so it is a warning sign that you have a cake. Then after that, we're gonna talk about pump pressure and its relation with mud weight change and its relation with pump speed change. Okay. Then gonna talk about shut-in procedures if we already have a cake. So how to deal with this situation, okay? We have two types of shut-in. We have hard shut-in procedure and soft shut-in procedures, okay? Then after shutting the well, how to deal with the situation, how to kill the well. So we're gonna talk about killing methods. We have conventional methods and unconventional ones. So about conventional, we have driller method with S2 circulation, first circulation, second circulation. Also, we have weight and weight method, okay? This is for conventional method to kill the well. After that, we're gonna talk about the unconventional one, like what? Like the volumetric method, how to deal with volumetric method and how to conduct it properly. Also, during killing the well, okay, we may face some challenges, some problems, like what? Like shock push out, like shock plugging, like nozzle plugging, like nozzle blown out. So we need to deal with all of these situations, okay? After that, we're gonna talk about something called hydrate, okay, and ballooning, formation ballooning, and kick tolerance. Then we're gonna finish our P&P part, principle and procedures, by talking about drills. The drills have been conducted in the well side to make training, to make your crew effectively able to recognize and deal with different situations like a kick, like tripping, okay? This for our first part called P&P, principle and procedure. We have 2 days for principle and procedure. Then the third day, we're gonna talk about the equipment part. So in equipment part, we gonna pass through the POP stack. We're gonna talk about annular, the different types of ramps, drilling spool, and the stack itself, and pressure test for the stack, okay? Then also have a discussion about the diverter, about pressure test for all equipment, and the equipment used in pressure testing, okay? So after that, we're gonna pass about the COM unit and accumulator unit, the source of pressure, okay? How to run on the oil and the rig side. Then we gonna talk about the tools used in case of tripping, like drill pipe safety valve and inside POP. Then we're gonna finish by talking about the connection and flanges type and the ring gaskets also, okay? So let's have a look on our course. It will be divided into 4 days, and the 5th day will be your final exam. So at day 1, we're gonna talk about principle and procedures. Day 2, we're gonna continue principle and procedure also. And day 3, we're gonna talk about well control equipment, and we have something called simulator training. This simulator training will be virtual, okay? We gonna have a kill inside the well, so some influx just enters the well and we need to circulate it out of the well, and killing our well by driller method first circulation, for example. So we're gonna have a training for this situation, how to deal with kick situation. Then at day 4, we have a revision and some quizzes. We solve with you some exercises, and will be our virtual simulator exam on the 4th day. Then day number 5, you will have your final exam. So to pass this course and to pass the exam of IWCF level 5, level 4, you need to get minimum score 70% for both simulator and IWCF exam, B&B and equipment. So a quick notes about the exam. Exam will be 2 parts, B&B and equipment part. B&B will be 64 questions. So you need to get minimum score 70% for this part. Then you have equipment part. It will be 46 questions, and you need to get the same score, minimum score 70% to pass both of these 2 modules. Okay, guys? So this is for exam. But let me tell you something about our exercise book. Our exercise book is very, very important. All exercises, all questions in the exercise, all questions in the quiz book is a typical like what it comes in the exam. So if you need to get high score, and I mean 90%, 95, and maybe 100%, you need to focus more and more about our exercise, about our quizzes. All are typical like exams. So if you're gonna solve all of these questions and practice more and more about these questions, you get minimum score 90% at the exam. So let's start our course talking about first part, well control, principle and procedure. These are the three situations that we may face during our operation. Case number one, when we have hydrostatic pressure, the pressure of the column of the mud inside the well is equal to the formation pressure. So in this situation, we have balanced situation, okay? When we have our hydrostatic pressure, our pressure of the column of the mud is more and greater than the pressure of the formation. So in this situation, we in control situation. So formation fluids from the formation cannot able to enter the well as long as our hydrostatic pressure is greater than formation pressure. This is called overbalanced situation, okay? Once our hydrostatic pressure here is lower than formation pressure, so in this situation, formation fluids may enter the well, causing something called a kick. So in this situation, we have underbalanced drilling when our hydrostatic pressure is lower than our formation pressure. So here, once we are in underbalanced situation, so our hydrostatic pressure is lower than the formation pressure. So if you look here, formation fluids, this black dots will manage to enter the well, this fluids, okay, will manage to enter the well as long as the hydrostatic pressure cannot able to prevent them from entering the well. So in this situation, we have a barrier. Our hydrostatic barrier have been failed and formation fluids just enter the well, okay? As long as these fluids is still inside the well and didn't reach to the surface, so it is called a kick. But once our hydrostatic cannot able to keep them inside the well and we didn't take the correct action to shorten our well to control the situation, so formation fluid will manage to reach the surface. So in this situation, causing something called blowout. So what is the definition of the kick and blowout? Kick is an influx of formation fluid that causes the well to flow. But once these formation fluids reach to the surface, so in this situation, we have something called blowout. So it will be an uncontrolled exit of formation fluids at the surface, okay? Kick types, let's have a quick note about kick types. Kick fluids may be oil, may be gas, also may be water, okay? Also may be a combination of oil and gas. And the worst case, as you know, will be gas. When you have a kick gas, so this is the most dangerous case because gas is able to expand and is able to migrate. So it will make change of pressure of the whole system, okay? So to prevent the formation fluids from entering the well and also from reaching the surface, we have something called barrier. So let's have a look on the barriers, well barrier classification and the function of the barrier. The function of the barrier is to contain formation fluids and prevent it from entering the well and from reaching to the surface. This is the object of the barrier. We have three types of the barrier. First type is called primary well control. It is the use of the fluid, the hydrostatic pressure of the mud to prevent formation fluids from entering the well. So it's called the primary well control barrier. Once this primary well control barrier had been failed and formation fluids managed to enter the well, So it is the turn to the secondary well control or secondary barrier. It is the turn of equipment. It is the turn of the BOP, blowout preventer, to shut in the well immediately without any delay, not to allow the influx to be more and more, and not to allow influx to migrate and expand. Okay, this is the objective of the secondary well control barrier. A primary well control barrier have been failed, then secondary barrier, the BOP equipment also have been failed. So we didn't control the situation. So it's the turn of something called tertiary well control barrier. So the objective here of the tertiary well control barrier is to plug the kicking zone by drilling a well called relief well, okay, and a well in adjacent place nearer to the kicking well, and start pumping from it a special material, okay, heavy material, junky material, to plug this area of kicking. Okay, so let's share with you a whiteboard for more clarification. For example, if we have here our well, okay, and we have, sorry, and we have here the drill string, okay, so we shot in the well on a kick. The well is filled with mud like this, but this mud hydrostatic pressure cannot able to maintain or overcome formation pressure. So formation fluid just enters the well and managed to overcome the hydrostatic pressure, then managed to overcome the BOP and reaching the surface, causing something called blow out. So in this situation, we need to drill another well in a nearer place like this and make a direction into the kicking zone like this and start pumping from it, okay, heavy material and special material into the kicking zone to keep plugging it and prevent it from more kicking and from more formation fluid to enter the well and to reach the cells. Okay, so this well is called relief well, RELIEF well. Okay, this is for our tertiary well control barrier. Back again to our presentation. Here we have another classification for our barrier. We have procedural or operational barrier. Okay, so what is the operational barrier? During the normal operation, your eyes, when monitoring the well for any gain or loss, this is called operational barrier. I mean, you need to check the gain and the active bit for any gain or loss by your eyes. Then we have something called physical barrier. So physical barrier, anything you can see by your eyes and touch, okay, like what? Like cement plug, like the BOP, like the drilling mud, okay? Then we have mechanical barrier. So what is the mechanical? Mechanical barrier is a piece of equipment that contains the flow from the formation. Like what? Like the unperforated casing. Once it is cemented against the formation, so no formation fluids will be able to enter the well. Then we have barrier system and barrier envelope, okay? More than one barrier acting together in place to contain fluid and contain the flow from the formation. So in the normal situation, in the normal drilling operation, we have barrier system with two barriers. First barrier and primary barrier will be our hydrostatic pressure of the mud, okay? And the secondary one, second one, will be our equipment, our BOP stand, okay? This is for barrier system and envelope. But according to API policy and well control instruction, no barrier cannot called as a barrier till passing a pressure test. So a barrier can be applied and set in the well till passing pressure test. You need to pressure test your barrier to check if it's possible to use it or not. So what is type of pressure test? We have two types of pressure test. We have positive pressure test and negative pressure test. So as you know, positive pressure test here is to apply pressure on the surface side of the barrier more than of the formation side. And the negative test is to apply pressure in the direction of the formation side more than the surface side of the barrier. Okay, so let's share with you whiteboard for more clarification. We have here our well like this. Okay, we have here our drill string. Okay, so we have here a cement plug like this. We have here cement plug. Okay, and we need to test this cement plug. So we have two types of, we have here cement plug. Okay, we have two types of pressure test for this cement plug. So we have positive pressure test and we have negative pressure test. Okay, when taking this cement plug, okay, as individual here, so this is the cement plug. We have two pressure applying on the test plug, pressure from above, from the surface side, and pressure from below, from the formation side. Okay, so this is pressure from surface side, and this is pressure from formation side. For positive pressure test, you will apply pressure from surface side more than the pressure from formation side, and wait some time from 5 to 10 minutes to check the barrier is not leaking. Your pressure is stable. Okay, no drop in the pressure tweaking. Then for negative pressure test, we have the same thing. We have here the cement plug individual and separated. Okay, also we have two pressure affected this cement plug. So we have pressure from above, pressure from surface side, okay, and pressure from below, pressure of formation side. For negative pressure test, you will make the pressure from formation side will be greater than pressure from surface side. We can make this situation in this case by making displacement for the fluid inside the well with lighter mud. So we're gonna displace the heavy by lighter mud. So we're gonna decrease the hydrostatic pressure, causing under balance situation to be done. Okay, allowing formation pressure side, this one, to be greater than the pressure from surface side. Okay, so these are the two types of the pressure tests: positive pressure test and negative pressure test. Okay, so what is the recommended test, positive or negative, guys? Positive pressure test is recommended or negative pressure test?
I think the negative one recommended.
Yes, the negative pressure test is recommended because it is in the direction of the flow. So here, this is the formation pressure. So as long as your cement block, this one, will be able to withstand the pressure and overcome the pressure from the formation side, so it will be more stable when had been set in the well and preventing formation fluids from entering the well. So back again to our presentation here, negative pressure test is recommended to perform the test of the barrier. And as we mentioned, we need minimum to test the barriers in place. This is called here barrier system or barrier envelope. Two barriers acting together in place. Also, according to the API recommendation, we need to make pressure test for the most important 2 points, the cement block and liner lab, to check their integrity. Why these 2 points specifically? Let's back again to the whiteboard. Here we have the 2 cases and the 2 scenarios. Case number 1, when we have the drill string inside the well. Okay, case number 2, when we have a liner. Okay. So here, first case, we have cement block inside the well, and below is the formation. So here will be formation, and formation fluid. Okay, the same thing here. We have formation. Okay, so why we need to pressure test these 2 points? The point of cement block and the point of liner lab. Why these 2 points? Because these 2 points are points of communication. So it may allow the formation fluid to enter the well. So here, once the cement block has been filled, so formation fluids will manage to enter the well. The same thing here for liner lab. Once this point is leaking, so formation fluids will manage to enter the well from these 2 weak points or points of communication. So the most important 2 points we need to check their integrity will be cement block, and the second one will be our liner lab. Okay, guys? Let's back again to presentation. Now we're gonna talk about pressure concepts. We have 2 pressure, 2 main pressure. We need to talk about them: hydrostatic pressure and formation pressure. So starting by hydrostatic pressure, here hydro refers and related to fluid, and static refers to fluid at least, as you know. So how to calculate hydrostatic pressure? Hydrostatic pressure will equal mud weight times TVD times constant. Okay, so we have here units: pressure in PSI, pound per square inch, here mud weight in ppg, pound per gallon, and depth in feet. So how to convert ppg times feet, okay, into PSI, pound per square inch? By using this conversion factor. So the value of the conversion factor will be 0.052. We use this value of conversion factor, okay, to convert ppg times feet into pound per square inch. It's called conversion factor, and it's equal 0.052. In our hydrostatic pressure, we deal with the TVD only. So here we concern about the TVD and not concerned about the shape of the hole. So the shape of the hole does not matter. If you're gonna calculate hydrostatic pressure at these 2 points, at these points, okay, at the lowest part of all of these shapes, we're gonna find that hydrostatic pressure here equal hydrostatic pressure here and equal for all shapes at the same point, as hydrostatic pressure only deals with TVD, not deals with volume, not deals with measured depth. And here is the difference between TVD, true vertical depth, and MD, measured depth. Okay, guys, you know the difference between the true vertical depth and measured depth.
Yes.
Okay. Now it is time to talk about something called hydrostatic pressure gradient. If we have hydrostatic pressure for this shape, for example, equal 6,000, okay, 6,000 psi, and we have its length or TVD equal, for example, let's share with you whiteboard. So if we have here for a specific well with TVD equal, for example, 3,000 feet. Okay, so to calculate its pressure, we need to know the mud weight inside the well. So say 9 ppg. Okay, so this is our well. So here our hydrostatic pressure will equal 0.052 times 3,000 feet times 9 ppg. Okay, let's calculate it. Let me check with you. It will be 0.052 times 3,000 times 9 ppg. So it will equal
14.
Yes, 1404 psi. Okay, this is for hydrostatic pressure. So what if I ask you to calculate something called pressure gradient? Hydrostatic pressure gradient.
And
So
we will divide it to total vertical depth, right?
yes. So we need to take the hydrostatic pressure over the TVD. So it will equal also, if we gonna take hydrostatic pressure over the TVD,
0.48.
so it will equal 0.52 times mud weight. This is the equation to calculate the hydrostatic pressure gradient from hydrostatic over TVD. So it will equal here the rest of the equation, 0.52 times the mud weight. So here to calculate the hydrostatic pressure gradient for this real case, so it will equal 1404 over TVD 3000. So it will be, let's calculate, 1404 over 3000. So it will be equal 0.468, right?
Yes, right.
0.468 psi per feet. Okay. And we have another way to calculate hydrostatic pressure gradient by just times 0.052 times 9. Okay, these two factors. Let's change the color. This one, 0.52 times 9. The rest of the equation. We have the conversion factor and we have here the mud weight. Okay, so if we times 0.52 times 9, so we're gonna have the same value, 0.468 psi per feet. So this is for hydrostatic pressure gradient. Back again to our presentation, but here we have some questions for you. Please check. Here, he gave you that 10 ppg and need to calculate pressure gradient. Could you please calculate this, please? If we have mud weight 10 ppg.
0.52.
Okay, right. So example number 2, if we have pressure gradient at 8500 feet is 0.65 psi per feet. So what is the mud weight in this situation? We have TVD and we have pressure gradient. So it will equal.
Excuse me, I got interrupted. Can I get the question again?
Okay, here we have TVD as 8,500 feet, and we have here our hydrostatic pressure gradient. So to calculate the pressure in this situation, we need to just times the TVD in feet.
12.5, I guess.
Yes. So here, just take the pressure gradient over 0.52 to calculate the mud weight. So it will be 12.5. You calculated right this?
Yes.
Okay. Now we're gonna talk about the formation pressure. So what is the formation pressure, guys? Formation pressure. Formation pressure, it is the pressure of the fluids inside the formation pore space. So if I ask you about the definition of the formation pressure, it will be the pressure of the fluids within the pore space of the formation. Here we have a specific datum to classify the formation pressure gradient into normal, abnormal, and subnormal. When we have formation pressure gradient equal 0.465 psi per feet, okay, so it will be normal. Once you greater than this value, so you will be in abnormal pressure. If you below, you will be in subnormal pressure, okay? And we have many more causes for formation to be abnormally pressured. Here, as we mentioned before, the difference between overbalance and underbalance, when the formation pressure gets larger than hydrostatic pressure, so we are in underbalance situation and formation fluids will enter the well causing kick. Then if we didn't control the situation, we'll have a flow out. So here, let's have a look on this question before calculations. We have formation pressure at 1,002 feet equal 601 psi and mud weight equal 10.5. This pressure will be normal, abnormal, or subnormal.
I guess it will be abnormal.
Abnormal formation pressure. We need first to calculate the formation pressure gradient. So it will be 0.5008 psi. So this value will be greater than the specific datum, the normal one, 0.465. So here our formation is abnormally pressured. Okay. Okay. So what about this question? What is mean by abnormal pressure related to the fluid pressure in the formation? Could you check this question?
I think it's C.
Yes. When formation fluid pressure exceeds formation water hydrostatic pressure, so in this situation, we can say we have abnormally pressure formation. Okay. Now we're gonna talk about the causes that cause the formation to be abnormally pressured. Number one, we have something called undercompacted shale sand. Okay. During the sedimentation of the formation and the compaction of the formation, we have dewatering process. This black arrow means there is dewatering. I mean, water started to be out of the pore space of the formation, okay, with compaction. So once we have here a impermeable formation or impermeable layer like shale formation, so this shale formation will prevent the pore space filled with water from more dewatering, so causing trapped pressure in this area like this. Here, formation pressure will be abnormally because the sealed area here of shale, okay, prevented more dewatering, prevented the formation from expelling out the water from it, okay? So here will be abnormally pressured formation. So if we plan to drill a well in this area, we need to take into consideration the cause of abnormally pressure, okay? We can determine it by seismic, by geological, and reservoir engineering, okay? So here, if you look to this trend, to the pressure, once we phase this area, we will find a shift in the trend of the pressure refers to the abnormally pressured formation, okay? This is the most common cause of the abnormally pressured formation. Cause number 2 is called gas cap rock. So what is meant by gas cap rock? Here we have sealed formation like shear, impermeable formation, and below it there is gas. Why gas in this area? Gas is lower dense, so tends to move upward, okay, due to its lower density. And once it faces here the impermeable formation, so cannot able to go through it and move upward again and again, okay? So in this area, there is trapped pressure caused abnormally pressured formation. So how to calculate the pressure at the top of this area, okay? This question may come in the exam, asking you to calculate the pressure here, the abnormal pressure. So let's have a real example on it, sharing with you whiteboard. If we have here gas cap, this is surface side, and we need to drill a well in this area. So we need to calculate the pressure at the top of the gas cap, okay? And here is normal formation. We have TVD, for example, 3,000 feet, okay? So here at the middle, we have 1,500 feet, okay? And we need to calculate the formation pressure. Here, for the case 1, let's change with you color. Case number 1 to calculate formation pressure here, and case number 2 to calculate formation pressure at the top. We have here gas inside or below the gas cap rock or the cap rock with hydrostatic pressure gradient 0.1 psi per feet. So first scenario to calculate pressure here at 0.1. So here formation pressure at 0.1 will equal the normal formation pressure gradient 0.465 psi per feet times 3,000. Okay, so let's calculate with you 0.465 times 3,000. So it will be 1395. It will equal 1395 psi. Okay. So if we need to calculate pressure here at the gas cap, we need first to put its equation. V abnormal will equal formation pressure minus the hydrostatic pressure of the gas. So here it will equal the 1395 we just calculated here, this value, okay, minus the hydrostatic pressure of the gas. To calculate hydrostatic pressure of the gas, we need to take its TVD 1,500 times 0.1, so it will equal 150, okay? So here it will be 0.1 psi per feet times 1,500. So it will equal, let's calculate with you, the same number minus 150. So it will be 1,245. Okay, this is for abnormal formation pressure. Okay, let's have a look if we ignore the abnormal pressure cause and calculate it as normal. So normal pressure at point 2 will equal what? Will equal 1,500 times what? Times 0.465. So let's calculate. It will be 1,500 times 0.465. So it will be only 697 psi. Okay, so let's imagine the difference. How much is the difference between the abnormal pressure at point 2 here, abnormal pressure here at point 2 when we calculated? So it will equal, as we mentioned, about 1,245, and here equal 697. Okay, so there is large difference between two values, about 500 psi. So if you ignore the concept of abnormally pressure formation and you're gonna drill and plan to drill a well in this area, okay, of the gas cap, so you need to take into consideration the gas cap reason, and if you ignore it, for sure you will have a kick and being an underbalanced situation. Okay, clear till now, guys?
Yes.
Okay. So here, as we mentioned, to calculate the pressure at this point, be abnormal, we need to take the pressure of the formation here, the normal formation pressure, minus the pressure of the gas below the cap rock. Okay, so pressure here will equal 0.1 psi per feet times the TVD at this area. Cause number 3 called surcharged formation. Here, once we have bad cement job, okay, so this bad cement job making communication, no isolation between zones. So always the lower formation here, always charging up the upper formation with fluid. So if you're gonna drill here a well without taking into consideration this cause, you will find here abnormally pressure formation. So if you plan to face for example, 2,000 psi formation pressure at, for example, 1,000 feet given depth, so you will find it more by 500 psi as greater than the normal due to the cause of the abnormally pressure formation, the surcharge formation 1. Here, cause number 3 and reason number 3, fault. And this fault is related to geological issue, okay? So tectonic movements or anything like this. Once we have a fault, the formation divided into two parts, one upward and one downward. So here, formation at downward has its same pressure, for example, 3,000 psi. Once you move the upward to a shallower depth, you will move with your pressure. So formation here, the yellow part, will move into a shallower depth with its pressure. So if we have here 3,000 psi, we'll have the same 3,000 psi at shallower depth. So if you plan to drill well here in this area, it will be normally, okay? It will be normal formation gradient. But if you're gonna drill well here in this area, you will face higher formation pressure at shallower depths. So you need to take into consideration always the causes of the abnormally pressure formation. Cause number 5 and the last one with us is called artesian well. So what is the artesian well? Artesian well is to drill your well and make your well here at shallower depths or lower depths than source of water. So once you make rigging for your rig here at lower depths than the source of water, always the source of water charging your formation. So if you gonna calculate your formation pressure, you will take the shorter TVD. Didn't take into consideration this part. So you always make your value of formation pressure lower than the actual, okay? So you need to take into consideration this cause of artesian well. So how to overcome this situation? From beginning, you need to make your rig side in upper position over the source of water if possible. And if it is not possible, you need to take into consideration this part called artesian well. Coming here to equation, so please check it. Okay, it's answered. So here, formation is overpressured by an artesian effect. What has created the overpressure? We have 3 answers, and the right one here will be the difference, the formation water source located at higher level than the rig floor, as we just mentioned in the previous slide. Now we're gonna talk about formation characteristics, okay, or reservoir characteristics. We have 2 main characteristics and 2 important characteristics that feature our formation. Number 1 is called porosity, number 2 is called permeability. So porosity here is the percent of the void space within the rock, okay, and it gives you indication about the rock capacity. So if we have here 2 rocks like shale and like sand at a given depth, for example 10,000 feet, so you will find the porosity of the shale around 8%, but the porosity about the sand at the given depth, same depth, will be about 20%, okay? This is because with compaction, shale is more compacted, so lower pore space, so lower porosity, okay guys? This is for porosity. And permeability here is the ability of the rock to transmit the fluid, okay, through it. We have many types of permeability, effective permeability and absolute permeability, but it's not related to our course. But you just need to know that the permeability is the ability of the rock to transmit the fluid through it. And the same thing here, if we look to this figure, on y-axis we have depth, and on x-axis we have here permeability. So once we have a given depth, 10,000 feet, okay, so we're gonna find that the shale equal 0 permeability, equal 0 Darcy. Darcy is the unit of the permeability, refers to the French scientist. And here, if we're gonna look to the sun, we will find that it's about 0.5 Darcy, and this is large number for permeability, okay? So if we're gonna have a look about the difference between porosity and permeability for you, here is our rock. We have some grains in the rock, some solids, okay? These solids forming the rock, and the spaces between the solids is called the porosity, okay? These spaces can be filled with fluids, whether oil, gas, or water, okay? So it's called a porosity, okay? And it's referred by this shape or this unit called phi, equal V pore space over V bulk. Okay, so this is called porosity. What about permeability? Permeability, if you have here grains like this, We have here grains. And we need our fluid to pass through the rock to enter the well. So formation fluid need to be passed through these permeable spaces or permeable formation to enter the well. So this is called permeability, the ability of the rock to transmit the fluid. Once there is blockage here, so fluids cannot able to move. Okay, so only the permeability happen in the interconnected pores. Okay, as you have interconnected pores, so the fluids found a way, found a path to move through it. Okay, this is the difference between the permeability, and we refer it by K, called permeability. Okay, so we have porosity and we have here permeability. This is the two main features of the formation characteristics or the formation features. Back again to our PowerPoint. Now here we're gonna talk about static and dynamic bottom hole pressures, okay? If you look here to this figure, you're gonna see the complete cycle of the fluid. First, we take the mud from active bed via the suction pump, then to the mud pumps here, then to standpipe manifold. So the fluids go to the standpipe, then to the swivel top drive system, and downward to the drill string till being out of the bed, then back from the annulus to the flow line. If you look here, there is a bend in the flow line. So the fluid at the surface at this point have 0 psi and only moves with gravitational effect. Then to shaker area here, then degasser, desalter, desander, then centrifuge again, and setting tank, then mud mixer here, then to the active bed again, and complete the cycle more and more. Now we have here our mud system, mud pressure losses. We have static bottom hole pressure. So static here means no pump is running, okay? So pump is turned off. So to calculate the static pressure here at this point, it will equal mud weight times 0.52 times TVD. So it will equal the mud weight inside the well 10 ppg and 0.52 the constant times the TVD 10,000. So the pressure at this point will equal 5,200 psi. Dynamic here refers pump is running. Okay, so once pump is running, I need to ask you a question, guys. What is the pump pressure? Pump pressure. You know? You know what is pump pressure definition?
I couldn't hear, please repeat.
I ask you about pump pressure. You know the definition?
I heard it, but I don't know exactly.
Okay. So pump pressure here is the pressure required to overcome all pressure losses in the system. So if you look here, we have here surface line, then drill string, drill collar, then from annulus to the surface. In the surface line, we have friction. Also in drill string and annulus, we have friction. So pump pressure is the pressure required to overcome all of these friction to allow your fluids to make its trip down the drill string and the upward to the surface again. So it's called pump pressure. So in the dynamic situation, we have annular pressure losses. Look here, in the surface line, we have pump pressure 2,600 psi. Surface line, we have pressure loss about 100 psi. Then down the drill string, we have 400 psi. Then in the drill collar, we have around 500 psi as a friction. You move downward and the friction upward, so you lose your pressure. And here at the pit nozzle is the maximum pressure loss, and it will equal to from 50 to 60% of the value, so it will equal pressure loss 1300 psi. Then back again to the annulus with annular pressure loss equal to 300 psi. Then back again to the surface with 0 and moving with its gravitational effect. Okay, this is for dynamic pressure loss. Here to calculate the BHP bottom hole pressure in case of dynamic situation, we need to calculate it by adding annular pressure loss to the static pressure. So as we calculated here, static hydrostatic pressure equal 5200 psi. To calculate the dynamic one, we need to add value called APL, annular pressure loss. This one affected in the annular area. Okay, so the increase is caused by annular pressure loss acting down on the bottom hole. Okay, this is called dynamic pressure. Here, if you look here to bottom hole pressure in various situations, we have here well is static, so bottom hole pressure only equal the hydrostatic pressure like this. But here for normal circulation, okay, during the dynamic situation, you will have hydrostatic pressure plus APL, annular pressure loss. Once you drilling in under balance or in well intervention jobs, so you use something called rotating head. So here your bottom hole pressure will equal hydrostatic pressure plus annular pressure loss plus rotating head back pressure. Okay, once you deal with kick situation, so you need to circulate the kick out, so you use something called a choke. This is choke, okay, can make back pressure. So bottom hole pressure in this situation will equal hydrostatic pressure plus annular pressure loss due to circulation plus shock pressure. Okay, this is for different situation to calculate and know more and more about the bottom hole pressure. Here we have to differentiate between static situation and dynamic situation. When we are in a static situation, so here bottom hole pressure will equal only the hydrostatic pressure 0.52 times TVD times mud weight. Then compare between hydrostatic pressure and formation pressure. If you found that your hydrostatic pressure is lower than formation pressure, so in this situation you will have a kick due to you are in under balance situation. But once you are drilling with higher hydrostatic pressure due to the effect of the annular pressure loss, so you always be in over balance situation and no formation fluids will enter the well. So the question here is for you guys. What is the minimum over balance pressure? Minimum over balance pressure?
I think it must be just above the 5,300 psi.
Yeah, the minimum over balance pressure according to the API recommendation and well control operation will be about 200 psi or equivalent 0.5 ppg. So the minimum is to keep your pressure greater than formation by 200 psi. Coming here to key definition called equivalent circulating density, ECD. Okay, this equivalent circulating density is theoretical increase in mud weight. So you use, for example, original mud weight 9 ppg in the static situation and the same in the dynamic situation. But in the dynamic situation, you have the effect of the APL on the bottom hole pressure. So we take this effect of APL and convert it to equivalent mud weight. So here, the ABL while circulating has the same effect on the bottom hole pressure as increasing the mud weight. So to calculate the ECD, we just put here the original mud weight plus the ABL pressure, converting it to mud weight or equivalent mud weight over TVD times 0.52. So for example, let's share with you whiteboard. Okay, if we have here our well, this is the drill string inside the well. We have our well is filled with drilling fluid or drilling mud. Say we have 9 ppg. Okay, so the mud weight will be 9 ppg. And we have the effect of the ABL, annular pressure loss, equal to, say, 300 psi ABL. Okay, we need to calculate the ECD, the equivalent circulating density. So here, ECD will equal to original mud weight 9 ppg plus the ABL 300 ABL pressure, annular pressure loss, over TVD. Say we have here TVD as 2000 feet times 0.052. So let's calculate, guys. It will equal 300 over 2000 times 0.52. So it will equal to, it will equal 9 ppg.
11.8.
Yes, plus 2.88. So it will equal 11.88 ppg. Okay, this is the ECD. Okay, and we have something called round for the mud weight and round for pressures. Okay, for mud weight, we need to make our mud weight only integral part. So say we have 15.1 decimal after the point. So here, for example, 1, 2, 3, not make it 11 or 21 or 31. So here, the ECD will make it round down, so it will be 11.8 ppg. Okay, this is for ECD. Back again to our presentation. We need to talk about the effects on pump pressure. The pump pressure and its relation with mud weight change and its relation with pump speed change. So let's have a look on the first situation. When we have mud weight change, what do you expect for pump pressure? It will be increase, decrease, or stay the same once you increase your mud weight, for example, from 10 ppg to 11 ppg. Pump pressure increase, decrease, or stays the same? Berkay, pump pressure increase, decrease, or stays the same?
I think it will decrease.
It will be increased. Once you increase mud weight, so you need more pump pressure to control the situation. So here it is good drilling practice to calculate the new circulating pressure before changing the mud weight. You need to change your mud weight from 10 ppg to 11 ppg. You need first to calculate your new pump pressure. So here the new pump pressure will equal the old pump pressure times mud weight new over mud weight old. Okay, so let's have a practice. Once we have changed our mud weight from 10 to 11, and we have all the pump pressure equal to 2,600. So pump pressure 2 will equal to 2,600, the old pressure, times the new mud weight over the old mud weight. So it will equal 2,860 psi. You can use it from the formula sheet also. Here, when we change pump strokes or pump speed, once we increase pump speed, so pump pressure will increase, decrease, or stay the same. Could you share, guys?
It will increase.
Yes, it will be increased. And you can calculate the new value of the pump pressure using this formula. Pump pressure new will equal pump pressure old over stroke per minute, or pump speed new over pump speed all power 2. Okay, and don't forget all power 2. So here, let's have a practice. If we change it pump speed from 80 SPM to 100 SPM, so we need to calculate the new pump pressure. How to calculate? Just apply the equation from formula sheet. Pump pressure new will equal the old pump pressure 2,600 times new pump speed 100 over old pump speed 800 all power 2. So the answer will be 4,600 or 4,063 psi. Okay, so I think there is a question for you now, so please have a practice on it. Now we have old mud weight, new mud weight, and old pump pressure, and we need to calculate the new pump pressure. Could you please calculate it?
It is 1,911 psi, I guess.
Yes. Once we applying the formula sheet number 10, so the new pump pressure will equal the old one times the new mud weight over old mud weight. Okay. So it will equal 1911 psi. Okay. So could you please check this question also?
With 30 SPM, it is around 2,600 psi, and with the 35 SPM, it is 3,539 psi.
Okay, you're right. Good. So the first thing here, we need to calculate the old pump pressure, adding all of these losses, then calculating the new pump pressure by applying the formula. Okay. Now we're gonna talk about the kick occurrence. So kick occurrence here, reasons why the formation pressure exceed hydrostatic pressure. We have two main reasons. First reason, when pore pressure increase will be abnormally pressure, and we discussed this earlier when we talk about the causes for abnormally pressure formation. Number one, we said that under compacted shale sand, under compacted shale sand, then gas cap rock, then faulted formation, surcharged formation, and artesian well. The 5 reasons for abnormally pressure. Here, cause number 2, when your fluid column reduced inside the well, so your hydrostatic pressure reduced below the formation pressure, so you will be in underbalance and formation fluids will enter the well. So here, this is the causes of the influx to enter the well. Number one, insufficient drilling fluid density. If you have a wrong mixing for mud formations, so in this situation, mud weight will be lighter than needed or than actual. If you're running the centrifuge too much time, so you remove more solids from the mud, so also your mud will be lighter. So in this situation, you have lighter fluid or insufficient drilling fluid density, so your hydrostatic pressure will be reduced, okay? And if it is below a specific value, so you will be in underbalanced situation and you may have a kick, okay? Cause number two here is called drilling fluid cut or gas cut. Once you drilling the formation, okay, gas from the formation, we have different gas type. Gas from the formation will enter the well, specifically at the time of the connection, and it's called connection gas. Okay, so this gas at the first instant has no effect as it is in solution with the drilling fluid if you use oil-based mud. But with circulation, when this gas approaches from the surface, so its volume will be greater due to expansion, okay, and take much volume inside the well, so reduce your hydrostatic pressure and you may be in underbalance and take a kick. So the best solution here is to running your centrifuge always to remove the gas and increase mud weight. So you need to increase your mud weight, not to being in underbalanced situation, okay? Cause number three here is called lost circulation. And I have a question. All loss of circulation cause the well to flow or cause the influx to enter the well? Or depends on something?
There is no return of the mud, and that causes really bad problems if you don't have enough material.
Yes, for lost circulation, if your fluids reach a level or drop to a specific level, and this level make your hydrostatic pressure isn't sufficient enough or isn't sufficient enough to control the situation and give you the required overbalance, so formation fluids would enter the well. So here, lost circulation dependent on the level you drop, okay? As long as the level you drop to give you higher overbalance or give you amount overbalance, so you didn't being an underbalance situation, so you control the well and no fluids will enter the well. Cause number four here, failure to keep the hole full. And this is the responsibility of the driller. The driller always need to keep the well full of mud, okay? Number five is called swabbing and surging while tripping. Swabbing when you make pull out of the hole or tripping out, and surging while running in the hole, okay? So while pulling out of the hole, you make suction effect, okay? So you have here momentary decrease in your bottom hole pressure, allow formation fluid to just enter the well. Once you stop the operation of pulling out, everything return to its normal situation. Here, surging while tripping, while running in the hole, so you add more pressure to the system, so may make some fracture in the formation, and formation fluids may enter the well, okay? Causing your level of hydrostatic pressure to be below the normal, so you may have influx inside the well. Always here also something called transition zone. So what is the meaning of transition zone? Transition zone here is a change in formation pressure from normal into abnormal. So while drilling into a formation and found that our rate of penetration ROP have a sudden jump from a specific point to another point. So for example, let's drilling with ROP 45 feet per minute, and At a specific time, we found a sudden jump to 80 and 90 feet per minute. So this is give us indication that we drill in abnormally pressure formation and we need to take action. What is the action? Is to make flow check. Okay, this is for transition zone, changing from normal into abnormal formation pressure. Here, surge and swap pressures. Swap pressure is momentary reduction on the bottom hole pressure, and this is the reasons of swapping. Pulling string too fast out of the well, small clearance and narrow annulus, so didn't allow the mud to return back to its place to the bottom, so causing momentary reduction on the bottom hole pressure. Balled bed or stabilizer, your bed is balling. Also high gel or viscosity mud. You can determine if you have a swap or not from the incorrect fill up. You need to follow your trap sheet, looking at the actual volume and the calculated volume and compare if there is no match between the two values, if no equally between the two values, so this gives you indication that you have swap. Okay, so you need to take an action, stop balling out of the hole, making a flow check, and if negative, run back to the bottom and circulate. If positive, you need to shut in your well immediately without any delay and start taking your procedure to strip to being below the influx and circulate out with the well with any of our killing method as we discussed later, inshallah. Then here, our surge pressure. Surge pressure is the same thing, but it's called momentary increase on bottom hole pressure. While running in the hole, you may running the string too fast, or there is small clearance or narrow annulus, balled bed or stabilizer, high gel viscosity mud. So here you may apply some pressure on the bottom and you may cause some fracturing and you may allow the formation pressure to just enter the well. Okay, here is the difference between the surge and swap pressure. While running out of the hole, causing the bottom hole pressure to be reduced, and in this situation, formation fluids will enter the well. Swapping or surging, sorry, when running in the hole, so we may add some pressure here, causing some fractures. So here, some from our drilling mud may enter the bore space here, causing the level to be dropped to a specific value. Then formation fluids will enter the well, causing a kick. Okay, guys? Okay, guys?
Okay.
Okay.
Okay, clear till now?
It's very clear.
Okay, so now it's time to have a coffee break, 15 minutes, okay? So 15 minutes and get back to you. Okay, guys?
Okay.
Okay.
Yeah, okay.